It is a pleasure to welcome you to the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is an pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. It is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. Today's lecture is on geophysics for geotechnical engineers, which will be delivered by Professor Carlos Santamarina, Dr. Andreas Pafuba and Mr. Craig Christensen. Carlos Santamarina graduated from National University of Córdoba and completed graduate studies at the University of Maryland and Purdue University. He taught at NYU Polytechnic, University of Waterloo and at Georgia Institute of Technology before joining King Abdullah University of Science and Technology. His team explores hydrochemothermomechanical coupled processes, and advances innovative characterization techniques for soils and fractured rocks, with applications in energy geoengineering and deep-sea mining. The team's research results are summarized in 2 books and more than 300 publications. Former team members are faculty members at more than 30 universities, researchers at national laboratories, or practicing engineers at leading organizations worldwide. Dr. Santamarina is a frequent keynote speaker at international events, a member of both Argentinian national academies, and has participated in several committees of the USA National Academies. He is the recipient of 2 ASTM Hodgkin Togler Awards, was the 2012 British Geotechnical Association Touring Lecturer, and delivered the 50th Turseggi Lecture in 2014.
Good morning, colleagues from all over the world, and Professor Das and Dr. Misra, thank you so much for the invitation to be here, for the introduction. It is really a wonderful honor to be part of this exercise. And I congratulate the organizers for such a wonderful initiative. I very much appreciate the words of Partha explaining the origin of this series and the goals of the series. With that in mind, I hope you can all see the screen, and I hope the screen is not flipping between one file and another, but otherwise, please do let me know. The purpose of this presentation today is to look into geophysical properties of soils. And from the beginning, we see that the word physics comes clearly into the picture. And so throughout the presentation, I have 3 or 4 goals. The first one is to explain the underlying physics in geophysical measurements. We need to understand what we measure in order to see how can we interpret it and use it. I will also give some hints as to how we can measure these properties, and I would like to emphasize that in general these are fairly simple measurements to make. However, I don't want to overplay that game, because actually the interpretation and some measurement biases can often be quite tricky as well. And finally, in every unit, I will give some examples of potential applications. There are plenty of publications in the literature, including ours, where you will find correlations and other applications. We have a short time, so I will highlight the underlying physics. These are the contents of today's presentation. Before we go any further into the geophysical measurements, I'm going to discuss a little bit about what soils are, because that will tell us how soils interact with these external stimuli. And then we will cover mechanical waves, electromagnetic waves, thermal properties, and we have these 2 new ones coming quite strongly into our field, which are X-rays and NMR. But I will close with some thoughts related to processing. At the key of geophysical measurements is fairly advanced processing, and I will provide some hints as to how we go about this. So let's start with soils. And so this is a very general word, but the fact is that somewhere the physics changes dramatically from fine-grained materials where capillary forces, electrical forces are important, and coarse-grained materials where particle shape and relative size is more important. And in fact, this division, which happens about the SIF 200, so the SIF 200 is a wonderful choice, is underlined by many other changes that occur across that size. So let's review some of them. For example, coarse particles are formed by mechanical processes, processes of crushing and abrasion and continuous impacts that change a material from being sharp and angular into a rounded material, the typical Ottawa sands. On the finer side, however, the formation history, the genesis, is completely different. There are lots of diatoms. For those of you who are near lakes, let's say Mexico City or anywhere around the oceans, these are the diatomaceous sediments and the foraminifera, etc. Look at the shape of fly ash, this circular shape. That is telling us that at some point there were droplets. This is when we burned coal. So thermogenesis. And then chemogenesis, where they form from precipitates. And these are the case of the clays, as well as plenty of crystals that we find in soils. So now we see that across the size, we also see different formation mechanisms, but also the forces that are acting on each individual particle change. And so at the large size, the self-weight of the particle is important. In the small size, electrostatic forces, that's the reason why dust gets on our furniture, and capillary forces play a more pronounced effect. Throughout the whole size, effective stress governs. The only difference is whether these other forces will come into play in addition to or not. And the last slide in this sequence, I want to remark what I said earlier. On the coarse size, the question is, are the particles rounded or angular? And do we have enough finer particles to fill in the voids, to increase the interconnectivity between particles and the stability of these skeletal units? On the finer side, the electrostatic interactions we were talking about, the van der Waals, the double layer repulsion, and the importance of the dipolar nature of the water molecule. Otherwise, none of these effects would happen. In the old times, we used to mix bentonite with carbon tetrachloride, an experiment that comes from the 1920s, to demonstrate that we lose complete plasticity when we do not use a polar molecule. We don't use carbon tetrachloride anymore because it is a carcinogen, but look for kerosene, or look for a molecule that has low polarity, and convince yourselves of the importance of water in the behavior of clays. So then that brings us to the revised soil classification system. We are very excited about this method because it's working very well. The basic unified soil classification system really got it so well in so many dimensions, but some of the choices made were not precise. And now we have 100 years of data, so we can do much better. And it's about occupancy of the pore space by the fines, and whether it is coarse control or gradually becomes fines control. On the left-hand side is all about the effect of pore fluids, and so we make liquid limits with water, water and salt, and kerosene, and we have a wonderful clustering opportunity to identify soil behavior. So in summary, folks, I think it is so important to remember what Terzaghi told us in 1920s. Soils are made of grains. Soils are granular materials, and everything else follows. The importance of size, of shape, of the pore fluids, of effective stress, compaction, the stiffness, dilation, strength, is all effective stress dependent. And then when we go into fines, it's all about how much surface they have, how small they are, specific surface, and the sensitivity to electrochemical and capillary forces. So with that introduction in mind, now we know what we are testing. And the next question is, what can mechanical waves tell us? And you can hear Pavarotti singing, and there is so much information that comes to our ears by sound waves. And so what is the origin of sound waves, and what can they tell us about soils? Well, everything is about Newton. F equal ma. This is mass density, m. This is acceleration, the double derivative of a particle displacement with respect to time twice. This is ma, and this is the force across an element. And so from here you see that there are two modes of propagation. One is varying longitudinally in X, and the other one is varying transverse with particle motion in Y, but propagating in X. And so we have two modes of wave propagation. I couldn't get the picture to be precise, but you see these are pendulums hanging from a wall, and if you displace a particle transverse to the position of the pendulum and the pendulum are interconnected by little springs, then this perturbation will propagate to the right while the particle continues vibrating in the Y direction. A longitudinal wave is when I have the same sequence of penduli, but now I displace one in the same direction as the alignment, and they are connected with little springs, which is the contact stiffness between particles. And so this perturbation propagates to the right, but the particle motion is in the same direction as the perturbation. And so this is called a longitudinal wave. How do we measure that? Very simple. Bender elements, piezo crystals, resonant column is a sophisticated way, but if you need attenuation, if you're into earthquake engineering, etc., is the most reliable way of getting attenuation. Otherwise, for velocity, you're perfectly fine with standard piezo crystals. You need some type of a source. Piezo crystal can do it, but in the field, we use other bigger sources and geophones. In all cases, you need an amplifier, an A to D converter, let's say an oscilloscope, and some storage capabilities. Very simple setup, very powerful measurement. So the next, I will not mention anything about attenuation because we don't have much time, but I will talk about S waves and P waves. And because S waves are telling us they propagate by shearing through the skeleton, not by decompression, otherwise water plays a critical role, we're going to say quite a lot about S waves. And so here we go. Let's assume that I have a column of a slurry, and at the bottom of the slurry I put two bender elements, in fact, in the vertical direction, so they are not affected by the self-weight. And we see how, as the column goes from being a slurry to being a sediment, how does the shear wave velocity become transmitted across the granular skeleton. And as you see at the beginning, there is no transmission, it's a fluid, and gradually the skeleton begins forming and the shear wave becomes stronger and stronger, and it travels in a shorter time. And some of these travel times are very long, folks. These wave propagations are less than 1 meter per second. We ride the bicycle at that speed. And so these are really very slow wave propagations at the beginning of the formation. And we see that in multiple experiments. Let's say this is blast densification. I'm not quite sure you can see the movie, but we blasted the soft layer at the bottom, and then the high pressure gets jetted out to enhance the ability of the soil to hold seismic action. And by the way, this soil eventually settled like a foot. Major densification took place, but for many minutes, in fact, for probably more than 60 minutes, the soil remained liquefied. So let's see what shear wave can tell us. Let's take this liquefaction tank. We put two bender elements. Before we whack it, we have wave propagation, transmission. The signal is quite noisy because we are not allowed to stack. These are short-time processes. And now we whack it and we lose the signal. The soil liquefied. And then as the pore pressure dissipates, the soil begins reforming and the signal appears again. In liquefaction, every time we liquefy a soil, we rebuild the soil from zero. And that's the reason why we can liquefy the same medium so many times, because it only densifies the very bottom of the column. The rest, it gets resedimented. This is powerful. And now we can do other things. For example, we can put geophones in our roads, and we can see what happens as a track approaches the location that we're measuring. And we see how the base, the granular base, gets stiffer and stiffer because the wave propagation gets shorter, the travel time gets shorter and shorter, and then the track passes by, and the wave propagation decreases. It's all about the stiffness of these contacts. And we have, this is data collected for more than 20 years from the literature and some of our own results. We have this Hertz-type power relationship that relates the state of stress to the shear wave velocity, effective stress. Therefore, we have this factor alpha and exponent beta, and depending on the soil, whether it is cemented, so beta goes to 0, low sensitivity to stress, or if you have Mexico City clays, we have completely different sensitivities to state of stress, and these parameters are correlated and help us tremendously in understanding the properties in the subsurface. But there are other forces that play between contacts. We already discussed the importance of suction. And so if you take a Bishop-type formulation, now we can add it to the effective stress produced by the boundaries, and we add the Bishop suction, and we can more or less approach what shear wave velocity does during drying. And this is not the soil water characteristic curve. This is the change in shear wave velocity as the soil becomes desaturated and capillary forces increase. Look, at the beginning we have large voids, but then as suction increases, it gets to the menisci, where clay has accumulated. This was a clay sand mixture. Clay has accumulated, builds up high suction, and the stiffness of our soil increases dramatically. Suction can play a very large role. But the most important part of measuring shear wave velocities probably is in the context of diagenesis and light cementation. Look, this is fly ash. We make a paste with fly ash, we put two bender elements, and we see with time how does the shear wave velocity increase. And we plot the shear wave velocity versus time, and we started with 100 meters per second. This was just a paste. And you see that the wave velocity passed the 400 mark. Even non-puzzolanic fly ash developed mild cementation, which has a huge implication on the ability of self-compaction. And as you will see next, not in this slide, in the next one, it may tend to collapse upon loading. Now, if the soil is cemented, then cementation at the contact takes over the stiffness of the Hertzian deformation. And so we become cementation control, and you may load the soil, but you don't change the stiffness much. You are in the cementation control regime. It is only when you load the soil very high that you go back to the stress control regime. But, as I hinted a few seconds ago, during loading, the soil may collapse. And that happens in fly ash, and it may trigger some of the failures that we have seen around the world. And the same in mine waste, in tailings. That early cementation hinders self-compaction, gives us high stiffness, but then as loading continues, the structure may collapse. And we see the collapse in the shear wave velocity. The last important observation I would like to share with you is that if you take a sediment, a sand, and you let it cement under confinement, let's say here under 400 kPa, we put some cement and we let it harden under confinement, the contact is squeezed by the effective stress. When you unload it, the contact gets stretched. Particles like a soccer balloon, they expand, and any cement that was in between gets broken. When you reload, you don't go back to the original stiffness. It's gone. This is the problem of sampling. And let me show you now sampling data. For sandy soils and clay soils, this is the velocity in situ, and this is the velocity loss, the ratio of the velocity measured in the lab compared to the velocity measured in the field. And particularly in sandy soils, we tend to have a very pronounced decrease in shear wave velocity after sampling, factor of 2. The stiffness will become a factor of 4 if you're thinking into settlement computations. In clays, the effect can be tricky because in soft clays, during sampling, you may actually consolidate the clay and give you higher stiffness. sampling is a major problem, and on the contrary, is a major advantage for the use of shear waves to know what is the stiffness in situ. But talking about using this to make settlement computations, I would like to caution you of the following. Let's follow this experiment from Diagenesis and Atkinson, wonderful data now from 25 years ago. And during triaxial testing, they measured the shear wave velocity at different points. And so this is how the shear wave velocity evolved. Even near failure, the shear wave velocity didn't change much, or the shear modulus in this case. Now, I curve fitted here with a hyperbolic model just to get a smoother trend, and I plot the tangential stiffness along the path, and the tangential stiffness clearly drops. This is our hyperbolic modular degradation curve. So be careful, because load deformation is a process of continuous change in the soil structure. However, wave propagation is an instantaneous measurement of a stiffness and does not involve change. Two completely different processes. If we use shear wave velocity for settlement computations, we have to do it in the context of proper modulus degradation. I will say something about P waves, and this is the logic of P waves. Is a constraint modulus. This is from theory of elasticity, the constraint modulus, and this is the which is a function of the bulk modulus and the shear modulus. Now, I can begin doing this cascade of analysis. The bulk modulus of the soil is the bulk modulus of the skeleton plus the grains and the fluids. And so these are the grains and the fluids, but the fluids may have water and air. And so I do this cascade and I fill in this equation. I do the same with the mass density. And this now is going to tell me something important about P waves. P waves have huge, any presence of gas will have a huge effect on the P wave velocity. In fact, this is a soil with bacteria, and now we will feed the bacteria with nutrients, and the bacteria will begin making bubbles, typically CO2, or in this case nitrogen, which is not very good. It becomes quite contaminant. But so these bubbles now soften the stiffness of the water. And you detect that with P wave velocity very well. And then a bubble escape, and then new bubbles begin getting formed. But this is the main contribution of P waves for our purposes, which is the soil truly saturated? And by the way, you can go back to Ishihara, and you can see the cyclic resistance ratio. As soon as you have any gas present in the pore fluid, your ability to resist shear, cyclic shear, increases quite significantly because of the compressibility, the compliance of gas bubbles. But P waves are amazing if you are in offshore, and marine seismic is exceptional. Sub-bottom profilers are exceptional. Here we were checking the foundations of a long bridge after the Katrina scouring effects, and you see the scour next to every pier, every foundation. And this is the famous Storegga landslide. And look at the magnitude of this landslide. And this is 12,000 times bigger than the Bayonne landslide. This is huge. And you can visualize it so beautifully with bathymetric measurements. And there is so much we can do today with bathymetric measurements. So for those of us who are doing geotechnical engineering with applications offshore, measurements with P waves are certainly very powerful. So folks, this is a brief summary of what we can do with P and S waves in our field. These, first of all, are small strain phenomena, great for monitoring processes. The shear wave is all about the stiffness, the shear stiffness of the skeleton. There are excellent ways of measuring that in the laboratory and in the field. The P wave is a lot about how close we are to full saturation. And together they complement each other, and they give us complementary information that we can use to enhance our understanding of the sediments. I'm going to speed up here because we're going to run out of time, but The next section is about electromagnetic waves, and then we see the beauty of nature because it's all about electromagnetic waves. And everything comes from Maxwell's equations, and this is the wave equation. It has one more component than the standard elastic wave equation, and that is our problem because that can make it very attenuating, and it will not go deep enough into our soils. But the most important thing I would like to highlight here is that there are three parameters: the magnetic permeability, the electrical conductivity, and the permittivity. And I would like to tell you what each of them are telling us about the soil. But before I go any further, let me just say that, once again, they're relatively simple to measure. In some frequencies, the only thing that you need is an oscilloscope and a signal generator. You can replace that with more efficiently with an LCR meter. With higher frequencies, you will need a network analyzer or a vector analyzer. For more field applications, we have TDR, GPR, electrical resistivity tomography, a wide range of EM and induced polarization techniques, all based on pretty much the same concepts: an oscilloscope and a signal generator. So what do these properties tell us about the soil? For their application, there are two things that we need to keep in mind. We need to compute velocity, and we need to have enough penetration. For example, you cannot put a very large potato in an oven because it will not cook the center because there is not enough skin depth in a microwave oven. And infrared radiation only touches the skin of our surface. It doesn't go inside. So different ways we have different penetrations in the material. So here are the two equations that we will need to use. One for wave velocity and the other one to anticipate whether the technique will go into the sediment or not. In general, we assume that this quantity, the permeability, the magnetic permeability, is 1, meaning that the soils are non-ferromagnetic. That is 90%, 95% of the cases true, but sometimes it may surprise us. And so this is all I'm going to say about the magnetic permeability. Please do take, this is the case, this is a major failure in the US, probably one of the worst environmental disasters, the Kingston fossil plant. This is all fly ash, and it ran downstream. We took some of the specimens, we were doing some measurements, they were not behaving well. So this is what we did. You put some dry powder on top of a piece of paper and you rub a magnet underneath. And when you rub a magnet underneath, if the particles move, that means that you have magnetic particles and you cannot disregard ferromagnetism. So that is as simple as that. You don't need more sophisticated measurements. If the particles don't move, then you can assume non-ferromagnetic conditions. So then the next parameter is, what is electrical conductivity? Well, electrical conductivity in our cables is all about the movement of free electrons. But we don't have free electrons in water and minerals, and so I apologize, I will close it off. My apologies. I guess that these are some of the consequences of distance online communication. So, but we don't have the movement of free electrons in minerals and in water. So what is moving? Well, when we put salt in water, the salt dissolves. Let's say that this is sodium, the red one's chloride is the green. They dissolve and they get surrounded by water molecules. These are hydrated ions. And these are the ones that are going to move the cations towards the cathode and the anions toward the anode. And this movement of charges is what electrical conductivity is all about. So then the electrical conductivity of the pore fluid will be a function of the concentration of ions, the balance of the ions, their mobility, and some Faraday's constant to get the units right. Now, what happens in soils? Well, electrical conductivity in soils has two contributions. One is the salt water, the water with ions inside the pores, but of course it's going to be diminished by the fact that this pore fluid is only in the pores, so it has to be multiplied by the porosity, and if you don't have 100% saturation, it has to be multiplied by the saturation. So it's very simple. This is the electrical conductivity of the soil. Caveat: if you have a soil with lots of surface, that means a clay, we form these double layers around clays, and these ions in the double layers can also migrate from one particle to the other. And so this counter-ion cloud of the double layer is another contribution to the potential conductivity, and so it's going to be a function of the specific surface of the soil. And it's only going to come in when soils have high specific surface. But the evidence is very strong. So this is a sand, typical sand for different sands, for different porosities, and that is Archie's law. Go back, Archie's law is not a law, it's just this equation with few other fitting parameters. It's all about porosity and electrical conductivity of the pore fluid, with a couple of fitting parameters to give a little bit of curvature. But in the case of soils with high specific surface, then this component kicks in. And so be careful. Archie's law should not be used blindly, particularly when you have clays and pore fluids with low ionic concentration. Let's say you are in rivers and lakes, low ionic concentration. That becomes, we have to be more thoughtful than just Archie's law. So what can we do with electrical conductivity? Look, for the lab, this is a barred clay. You see the winter, summer, winter, summer, winter, summer layers of a barred clay. Now this is a hypodermic needle. We put an electrical conductor inside, we fill it in with epoxy, we shade it, and now we push it in. And as we push it in, we measure electrical conductivity continuously at the tip, and we pick up every single valve. Of course, this is upscale, and we can do it with a CPT. And very simple, a signal generator and a two-channel oscilloscope. We can go further, and we can put many electrodes and then do tomographic techniques to get a tomographic image. We can do this in the laboratory. We can do this in the field. That's one of the beauties of geophysical techniques. The same process pretty much can be readily upscaled to the field. Finally, I would like to speak about permittivity. And for permittivity, we have to keep in mind that it's all about how the water molecule rotates. It's the same mechanism that we use to heat the potato in the microwave. We rotate the water molecules. This is what we are doing with lower field intensities, but it's all about this for the most part. There are a few other effects, but for the most part, we should be paying attention to the rotation of the water molecules when we send an electric field. And so it will be proportional to how much water we have. Here we are squeezing a clay, we're running a consolidation test while we monitor the permittivity, and you see the effective stress increases, the volumetric water content decreases, the permittivity decreases. If the water freezes, whoa, very easy to detect with permittivity. If the water gets contaminated with air, gases, any DNAPO, LNAPO, very easy to get detected. So these are the things that we can do with permittivity measurements. And really, if you haven't used GPR, and there is a chance that GPR may work in your sediments, it needs to have enough skin depth, then it is amazing what you can detect with GPR. But you need the skin depth. And as we said earlier, depends on electrical conductivity. High electrical conductivity, where there is water and salt, or clays, will not give you that penetration depth. But look, when you don't have any of the above, the water is frozen, there is no salt, you can measure through 70 or 80 meters. These are these aircraft beneath 70 meters of ice, and you can see them through ice. Or you can see things through freshwater lakes. to the bottom of the ocean with GPR, a large number of cases with great applications. And because it's very sensitive to salt water, this is saltwater intrusion. Now with all climate change and sea level rise, measurements like this will become more important. This is where fresh water dominates. As soon as salt water goes in, it becomes opaque. So what can we do with electromagnetic waves? Keep in mind that it's all about penetration depth primarily, electrical conductivity, very powerful and robust, very easy to implement. And so we are going to be measuring electrical conductivity, ionic concentration, availability of water molecules freely to polarize whether it freezes or not, etc. Thermal measurements. Thermal measurements, there are a large number of thermal parameters. I'm going to focus only on one today because of its critical importance, and the other ones can be estimated much better. It is really about thermal conductivity. Now, what is temperature? Temperature is random vibration, molecules, random vibration. If you're in a gas or in a liquid, then they collide, and that's the way they transfer the thermal heat, thermal energy. In a solid, these random vibrations are not completely uncorrelated because the atoms are linked by little springs. So if this one goes up, this one tends to go up, down, more or less in some synchronicity, and this creates like a wave. They are called phonons. So in solids, phonons transmit thermal energy. So what controls heat conduction in soils? Well, this is an experiment. This is 1 inch diameter, 2.5 centimeters glass balls. And we put a heat source at the bottom. We apply a load, and we have a thermocouple in each of them, but we also have an infrared camera. And you see how the heat front of these phonons vibrating propagate from one to the other through the contacts. And so how do we do these measurements? You need a heat source, thermocouples, very inexpensive. For surface phenomena, infrared camera, but only for surface phenomena, but beautiful studies done within our laboratory chambers by the community using infrared cameras. But the bottom one is a source of heat and thermocouples. And then the rest, the mathematics is very simple and very robust. And so now we begin studying what controls the ability of the phonons to propagate from one particle to the other. Well, the higher the state of stress, the more you squeeze the contact, the better heat gets transmitted. And you know that because if you're going to grab a hot pot, you're not going to squeeze your fingers into it. You'll try to grab it as lightly as you can. And so effective stress, very important for heat conduction. And this is this curve here. Now, the other one that is very important is that if you're going to grab the hot pot, you don't do it with a wet cloth, because a wet cloth is very conductive, and furthermore, it's going to burn your fingers. And so that is the importance of recognizing the presence of water. Water itself is not very conductive, but water and the contact between particles help the phonons jump the void and get from one particle to the other. Summary. What is important for thermal conductivity? What is the mineral? The presence of water, you saw, plays a critical role. Let me go back and highlight that this was in logarithmic scale, and there was an order of magnitude jump. And by then, the presence of water says, who cares if you change the size of the contact or not by effective stress, is the presence of water that will govern. So the presence of water is very important. You don't need much. A little bit is enough to increase thermal conductivity a lot, because the water goes, by capillarity, goes into the contacts where it is needed the most. And of course, stress to flatten the contacts. But in addition, if you have fine grains filling in the void, these fine grains also create alternative flow paths, particularly if these grains are already beginning to carry the load, if you have 40% of them. And together all these control the number of contacts, the coordination numbers per particle, and the quality of the contact. And in fact, this is coming from Melbourne University, the thermal tiles and then putting heat exchangers in our foundations is becoming now a very important part of our geotechnical field. These are standard measurements and it should be done, it can be done in any laboratory and cell device. Closing thoughts about the thermal conductivity was captured in that equation. Just to add that all geothermal processes, if you're into nuclear energy from foundations to waste, climate change, urban settings, underground utilities is going to be very important. I said at the beginning that these are two tools that are becoming increasingly more used in our field, primarily for the laboratory, even though the petroleum engineering has been used in NMR in the field quite extensively. But I want to bring them to your attention. This is not just for sophisticated medical diagnosis. We can do this in our laboratories with great success. So let me start with NMR. This is nuclear magnetic resonance. That tells you exactly what it is. The nucleus, particularly the nucleus of hydrogen, well, they all have their spin, but this one is unbalanced. And so all these little magnets are there spinning and moving. And so if you put an external field, you force them to align, and then you take them out of alignment and they come back gradually to that alignment. This is what nuclear magnetic resonance is. Now, every time by diffusion, these atoms or water molecules reach, for example, the walls of minerals, they get demagnetized. They lose that orientation, they relax. And so we can measure how long it takes for that demagnetization to take place, and that tells us something very important about pore size. So let me give you an example. This is kaolinite paste during drying. And during drying, we are losing water, and this is what the total magnetization that we are measuring is telling us. But where are we losing water? Now we analyze the spectrum of these vibrations, and we see at the beginning we lose the water in the large pores, but as drying continues, water remains only in the small pores. So this relaxation time is actually telling us pore size. It's a very powerful way to study pore invasions of immiscible fluids or including air. I wish I could tell you that the measurement is simple. It's basically simple. It's magnets and coils and some electronics, but we ourselves have not. We wanted to produce something that we can upload in our website and you can build that at home. It hasn't turned out to be that simple, but we promise that we're working on it. How to simplify the electronics is the key point. The other one is X-rays. Of course, X-rays have been around since Madame Curie and earlier, so more than 100 years. And embraced in our field early on, I have to say, in the 60s. But probably because of safety and cost, we have not used them extensively. Nowadays, this has become much more accessible. We have built our own micro-CTs. We have built 2 of them. And we have also purchased one, very expensive one. But you can do quite elegant tests with micro-CT. The upper 2, we did them in Grenoble, and these ones are now with our new micro-CTs. But look at this. This is a container with kaolinite paste after freezing. This is, you see, these are all the ice lenses forming like onion peels. And the center, because of cryogenic suction, the center became so dense that now ice cannot lens anymore. Just very few lenses. Everywhere else, ice formed lenses, like when an ice cream develop all the lenses. And so just amazing to see how cryogenic suction evolves. This is the insertion of a blade. It looks like the tip of a dilatometer. And even though we analyze this as an equivalent continuum, the sand, look, it's all about successive shear localizations. We can see how germination takes place, and then we make the soil transparent, and just by playing with signal image processing, we can see beautifully roots, how roots grow, and how, by the way, we can go back and put the grains, and you see how it displaced the grains as the root was growing. And yes, we can see how gas comes out of solution and eventually begins forming cracks within the sediment. And desiccation cracks happen not only from the top down, but they may also initiate and nucleate within the sediment. Exceptional opportunities. But all this requires processing, folks, and an understanding of these simple physical concepts and ability to process. And the last one I gave you was about tomography, and tomography may sound like a scary word, so let me show you how simple tomography is. Imagine that you don't know what is inside the body, but now we're going to have two long tubes, and I put a long tube here. This could be one borehole where we send elastic waves, for example, with a CPT or another better source. And we detect in another borehole, and we see that there is a shadow. In other words, waves were propagating very well, but then they don't propagate so well, and then again. So there must be something somewhere here preventing propagation. X-rays, P waves, S waves. Now, if we put now a source at the top, and we do the same, and we measure the shadow, now, there has to be something along this vertical line. So now if we superimpose the two shadows, this was the shadow caused, we back project the shadows. This was the shadow observed on the vertical borehole. This is the shadows, we're back projecting the shadows observed on the vertical measurements. Then the body must be here, and indeed, that is the body. We do this with projection from many different orientations, and this is tomographic imaging. And then I can actually say, okay, how long it takes to travel from one point to the other through one pixel and through the other pixel. Well, it depends on the length that this ray travels from this pixel and the velocity. And so I create a system of equations and unknowns. These are the measurements. I know the travel length, and what I do not know are the velocities in each pixel. So I just invert this matrix, and I solve the problem. It's the problem of tomographic inversion. By the way, they got Nobel Prizes for this. Powerful, huh? Amazing. It has changed medical diagnosis. It's changing our ability to do problems. And just to conclude, let me say that the opportunities when you mix geophysical measurements and a little bit of the mathematics of inversion are incredible. This is an old test that we ran. It's a cubical triaxial. Inside we put vendor elements, a very sloppy installation, I must add. But then we fill it up with saying, oh, but we put a party balloon here. And then after we loaded, we applied the stress control boundary conditions, and we inflated the balloon, and we could see shear wave velocity. Remember, shear wave velocity depends on the state of stress. So now we do a tomographic inversion of shear wave velocity, and we can get an image of the mean stress inside the medium caused by the inflation or deflation of the balloon. You have all been very patient, and so let me come to an end. In order to understand geophysical measurements, we are invited to really understand what soils are all about, and that is a good exercise for everything we do in soils. And we saw the importance of this changing physics, from the physics of fine-grained sediments to the physics of coarse-grained sediments. Take a look at the revised soil classification. Is really predicting very well this behavior. Then we saw the mechanical and electromagnetic waves interact with soils differently, therefore they give us different information. And this is the same as our eyes and our ears. They give us different information, and the same as our thermal sensors. And so together, they give us complementary information. We haven't lost any of the senses through the Darwinian selection process. That means that all the senses are very important to us, and they are not superimposing, they are complementing each other. The same with soils. Each of them tell us a different piece of information. not clearly related to our human senses, but truly geophysical, X-rays, NMR, and positron emission tomography. All these other techniques have a role to play, probably more in the laboratory than in the field. Give them a try. You can build most of these devices by yourselves with a little bit of understanding and ingenuity. And all this ultimately requires processing. So, to repeat some of the thoughts I just shared with you, these methods give us complementary information. They are based on physically sound concepts. And the advantage is that we can, in many of them, we can upscale them directly to the field. An electrical measurement in the laboratory or shear wave measurement is identical in the field. And that the parameters are critical to geotechnical analysis and design. These are low perturbation processes. Therefore, keep in mind, these are, from the point of view of wave propagation, mechanical wave propagation, this is small strain. So how you change it to larger strains is a tricky thing. But all these are low perturbation processes. An advantage being that you can monitor processes without disturbing them. So great for monitoring. If you do boundary measurements, with a little bit of mathematics, you can figure out what is happening inside. We can capture spatial variability and anisotropy in all these measurements beautifully and explore them, and these are major issues throughout the geotechnical field. And I didn't have time to, I had many other slides to show you the complexity of wave propagation, but in that complexity, there is also information, but we need to be aware of all that. But the purpose today was not to scare you, it was to tell you, go ahead, make it happen. And it requires processing. Folks, all this is the result of many group members, past and present. It has been amazing working with all of them. I have learned every day of my life. But above all, in this context, I'm so grateful to all of you for being here today, and Partha once again for the invitation.
Thank you, Professor Carlos, for that interesting presentation. We have some of the questions that are coming up, but I just wanted to mention that due to a limited amount of time, we cannot take generalized questions. So please keep your questions specific that can be answered within the time limit that we have. So the first question comes from Alonso from Peru, and he has two questions. The first question is that, what do you think about the definition of clay? Do you think that about the new definition based on its toughness is possible? And the second question is that, do you consider the current definition of water content measurement based on mass of the water to the mass of the soil appropriate to soft soils, or we need to redefine it?
Okay, there are lots of tricky things here, so let's see if we can dissect them a little bit. So let's start with clays. Folks, we tend to be often sloppy with the terms we use. And also, many fields interact. So words that we use in our field are different. Consolidated material for us is that we are squeezing a sponge. For petroleum people, is that the formation is cemented. So we use the same word in different contexts, but in particular in the case of clays, clays have two distinct semantics that we must not confuse. One is fine-grained sediment, typically less than 2 microns. But the other one is a mineral, the same as could be a diamond or a calcite. It's a mineral, it's a phyllosilicate. Phyllo means layers, and silicates, layers of silicates. So I think that we have the right terminology. We just have to use it contextually well. Let's keep, if at all possible, let's talk about fine-grained sediments when we need to refer to fine grains in general, to clays when we are particularly talking about clay minerals. It will reduce some of the uncertainties we have. With respect to water content works well, except for cases as follows. If you have materials which have voids inside, I showed the fly ash today, then is intragranular and intergranular water, And that also messes up our computation of void ratios. You are going to consider the voids inside the particles and outside, and specific gravity gets messed up. So, and the same would happen if you have organic matter that has absorbed water, and whether you want to take it into consideration or not. So, rather than suggesting a new formulation, what I would say is be very conscious of what you're doing and make sure that you're measuring what you think you want to measure.
Okay, the next question comes from Alezo, and he says, can you provide some comments on how to estimate the spatial distribution of early Diagenesis cementation in mine waste or fly ash deposits?
Yes, and we know that is a problem, and because the way for mine waste and fly ash, the way it gets deposited, typically with fluid flow, and then they are continuously changing the discharge. So it's going to create a very layered lenticular type of formation, and that will have lots of implications on the behavior of fly ash and how they fail, some of the catastrophic failures. Right now, the careful insertions with CPT, with high resolution CPT, is probably some of our best bet. But CPT is just a train to bring sensors to the formation. And so consider also placing, in some cases, electrical measurements may work very well. So the CPT with electrodes along the way can help you resolve some of the layering. You are not going to have check if you have enough penetration with electrical measurements, but probably you are not going to have with electromagnetics.
Okay, we can take perhaps one or two more questions. This one comes from Mayu, and he says that NMR seems the way to go for measuring moisture in subsoil. What are the limitations so far to push a NMR probe by a CPT or a DMT rig?
It has been done in basically they use the magnetic field of the Earth, and it has been done in the petroleum industry, but you can look into Schlumberger systems, but basically it's a larger body. I have not explored how far it can be downscale in size, but it is certainly worth exploring.
Okay, this one comes from Peter from Stockholm, and he says that they are planning to further explore the potential of UAS, RPAS, and flying drones as platforms for measuring. They're looking at a sensor fusion, which basically is a combination of thermal, AM, and GPR, that is simultaneous combination of different wavelengths, physical principles, etc. Do you have any recommendations in this context?
No, I think that data fusion is the way to go, and the only thing I would add to that is that I'm glad that you guys are doing this. The only thing I would like to add is that they do the interpretation very physics-based. That is, it's wonderful to have correlations, but the correlations should be physics-inspired. Let's get the physics right, data-driven, and that is where we do adjusting with parameters, but get the physics right. And let me extend that trend to laboratories. It is so easy to put electrodes, thermocouples, bender elements inside our odometers, inside our triaxials. Give it a chance. It's inexpensive. It can cost much less than the odometer or the triaxial. Give it a chance, because you're going to put your eyes, your ears, your sensors inside the specimen. It's going to be talking, and it's going to provide great information.
Okay, I think we can just take one more question before we close it. So this one comes from Priyanka from L&T India. I think she's from industry. So she has one question, that what type of waves can be used to identify the depth of soft sediments below the steeper material, say dense sand?
That's if you're working from the top, that's very difficult, and it's not the type of wave. Is the what is called impedance mismatch. When you see yourself at the mirror, it's because the wave went and came back. It reflected. And at the interface between a sand and a soft clay, you have a high impedance mismatch, and you're going to have low penetration for most type of waves. And in fact, even if you try to do it with Rayleigh waves, that creates typically all our inversion algorithms are for materials that get stiffer with depth. As soon as you revert that, then the primary mode of vibration is not everything moving in one direction or the other. It begins moving in higher modes, which makes the inversion more difficult for Rayleigh waves. So probably you will have to go in with some type of a probe.
Okay, this is the last question, I promise. So this one comes from Professor Alexander Soyman, who is from the Geotechnical Engineers Center at UQ. So Alex says that if we have to combine different geophysical methods to improve measurements, let's say, for example, void ratio, porosity, or moisture content.
Mm-hmm. Yes, I would start, if it is in the laboratory, I would start with a coaxial termination probe, like we have used extensively. You can see them in our papers, that sits at the bottom of chambers, because that is a very precise way of measuring the volumetric water content. Partha has similar techniques, the same technique. And then shear wave velocity. If you are concerned with the soil not being properly saturated, put a little piece of crystal, a flat piece of crystal to measure the P wave velocity is the best indicator of whether you have saturated the soil or not.